and sadness that we end our lectures today with sports.
So after suffering through the definitions of cyberwritten Hegel terminologies yesterday, today I would like to talk a little bit about like four manifolds and what do we know and what we don't know. The later will be like the part of the lecture. And so, of course, let's be ambitious. So how can we verify the existence of exotic structures in S4? So the existence of an exotic S4 is equivalent to have an exotic structure on D4. You just sort of, if you have an exotic S4, you just remove a little standard ball, open ball from it, and what you are left with should be an exotic D4, and vice versa. You can just close up an exotic D4 with a standard disk. So instead of shooting for that, let's study the problem here. And so here's a definition. We classify potentially exotic D4s into two classes. This is motivated by the definition from exotic structures on R4. So we say that X exotic D4, you understand what do I mean by exotic? It means that they are homeomorphic but not diffeomorphic. Is small if X embeds into the standard one. And X is large otherwise. And I need one more definition, which would apply to any four manifold with boundary. But I will just stick to this situation. So for an exotic D4 X, let's take Sx to be the set of all links in S3, which is just the boundary of X, such that, so this is a link, that L is slice. By which I mean that every component bounds a disk and these disks are disjointed. So I will try to draw. So this is my X. L is somewhere in the boundary. Now it has two components and both sort of bounds a smoothly embedded disk, which are disjointed. Okay, so here is the first statement, which there is the following. This is a simple observation that, so let's call it a proposition. We found it with Alberto Cavallo, former student, saying that if X is a small exotic D4, then this set of links is the same as for D4. I should point out two things. The first is that this whole discussion is very hypothetical. It could happen that we are talking about the empty set. But I think in mathematics, it's absolutely fine. But an engineer, this would be very disturbing. And if X is a large exotic D4 and X is geometrically simply connected, then Sx is strictly larger than SD4. So I should remind you that, of course, X as an exotic D4, it's homeomorphic to D4, so it should be simply connected. Geometrically simply connected means that it admits a Morse function with no one handles, no index on critical points. So this just tells you that with somehow measuring the slice genera of knots and links in X, we will never be able to distinguish a small exotic D4 from the actual D4. And at this moment, I have no idea how we would distinguish the two. So it's sort of tempting to expect that there are like no small exotic D4s. And I should point out that this has a strong relation to the Schoenflies conjecture. So here's a remark. The existence of a small exotic D4 implies the failure of the 4D smooth Schoenflies conjecture, which states that if we have S4 and we embed S3 in some differentiable way, then one side should be the standard D4. And of course, if you have an exotic D4, then a small exotic D4, then it would be false. I leave you to sort of sort out the details, but it's a very simple argument. So, there are so many conjectures in four-dimensional topology, and most of them you expect to be false, because there is like no good way to see any system. For me, this is an exception. I would think that actually the Schoenflies conjecture might hold, and that I expect no small exotic D4s to exist. I should give a remark here. So what are the chances to find an geometrically simply connected exotic D4 besides D4 itself? So this is remark number 2. There is an observation of Casson saying that if X is a contractible four manifold, with boundary, so I always assume that it is compact, it has boundary, and the boundary is not S3, then X is not geometrically simply connected. So, but of course, an exotic D4 has S3 as its boundary, so this principle does not apply. You should decide whether a large exotic D4 behaves more like a manifold with non-spherical boundary, or behaves more like a closed four manifold. And for closed manifolds, it's an open question whether simple connectivity implies geometrically simply connected. We don't know the answer. So after this, I would give you a sketch of the proof of the first statement. Let me just sort of label them. So idea for A, and I will not talk about B at all. So the idea is that if X1, X2 are two exotic D4s, and X1 is a subspace of X2, then Sx1 is in Sx2. So whatever link is sliced in X1 will be sliced in X2. And the idea is that being in Sx in general is equivalent to the following. Let's take the zero trace of L with the opposite, with the mirror of L. So this is just attach four-dimensional two handles along the components of the mirror of L with framing 0. So this is what's called the zero trace of this link. So L is sliced in Sx if and only if this embeds into X hat, which is just X closed up with the standard disk. So in the discussion session, we proposed this problem already, and I am determined we will propose it again until you just swallow it. Not for links, but for knots. And this is a very, very useful principle for understanding whether or not or a link is sliced in a four manifold. But notice, so let me just finish here.
Excuse me, what is the star that's
So okay, I can write mirror.
there?
Sorry. You're attaching 42 handles along what exactly?
And on the component of the, so this is what you do. So this is D4, and then you have your link. Again, it's only the component, and you just attach two handles with framing 0, and then you get this X mirror of L, and this has to embed into here. The argument is very simple, and you have to go through it once in your life, and then you will never forget. Or you do, but you think it's done. Okay, so I would like to argue for this. So suppose L is from Sx1, then we take this zero trace, and this is in x1 hat. So this is the picture. This is x1, d4, and then this space x and L is in here. This is x1 hat. But of course, it will not occupy the entire manifold. It will be somewhere here. And we just delete a small d4 disjoint from that. So that just means that XML is in X1 indeed, because X1 hat minus a disk, no matter which disk you delete, you will get back X1, but this is in X2, which is in X2 hat. So you have that this is inside here, so you get the right-hand side of the equivalence, so you get the left. So this is really a simple argument. And of course, if you apply it so this is the end of the proof. If X is small, it's a small exotic D4, then you have the containments. This is by definition of small, and this holds for every four manifold. Okay, so the lesson from here is that we might believe in the Schoenflies. The lesson from here is that we hope that there are geometrically simply connected counterexamples, or we should work on removing this condition. And then the message is that you really have to understand slice obstructions for links. And that might be a way to actually find a counterexample for the smooth four-dimensional Poincare conjecture. So you should pay attention when people are talking about like Kovanov homology and Higat-Fler and blah, blah, blah. Okay. All right. So we spent some time trying to understand the genus function on the first day, and we considered CP2 connected some with CP2 bar, S2 process 2, maybe CP2 connected some to CP2 bars. These are all manifolds where these gauge theoretic invariants are meaningful. You know, they remember that Seiberg-Witten theory is sort of attached to those manifolds where B2 plus 1 is even, right? This is where the moduli spaces have the right dimension to get something interesting. So what happens if we consider a manifold where this principle fails? So let's take 2CP2. We just connect some 2CP2s. The B2 plus invariant is 2. So you would expect that like nothing works. And then it turns out that things will work to some extent. So this is what I would like to explain now. So what is the genus function for this?
Are you CP2 bar or no CP2?
Now 2CP, so it's a typo. You know. In my file, CP2 is like CPK, and this is just CPKK. And so, you know, okay. It's in Hungarian. Okay, so what is the genus function of 2CP2? Well, we don't know. There is a naive guess. So here's the naive. So second homology of 2CP2 is just Z plus Z generated by the projective line in the first copy and the projective line in the second copy. And so we have alpha should look like D1 H1 plus D2 H2. And for simplicity, assume that D1 and D2 both are strictly positive. Then the first idea which comes to your mind would be that let's represent my class with the smallest possible genus in the first copy and the smallest possible genus in the second, and just tube them together, and let's hope for the best. So the naive bound, I don't know, naive guess, let's call it N of D1, D2 is just 1/2 D1 minus 1, D1 minus 2, plus the same with D2. If one of them is 0, then the formula is a little different because for the 0 class, you expect to be represented by a sphere, but this product would give you 1, and so you just sort of modify it in this way. So is there a chance that it should hold? And my argument is no. So let's see, what does it give for this class? Well, this is exactly what I excluded in the formula, but when it's 0, you expect the genus to be 0. So this would be 1, right? The 3 times H1 can be represented by a torus, 0 times H2 by a sphere. You connect some of them, and you get a torus. But I claim that this class can be represented by a sphere. And the construction is very simple. You just take CP2, and instead of representing the 3 times the generator by a smooth torus, you represent it by a nodal curve. The equation of this curve is just z times y squared equals x cubed plus x squared z. This is the homogeneous equation. It needs a little bit of a thinking that it's just the image of a sphere where 2 points collide. Okay? And in the other copy of CP2, you represent the 0 class by 2 lines. One of them with multiplicity 1, and the other one with multiplicity minus 1. And now we take the connected sum, and we tube these two together around their singular points. This is a positive intersection point. This is a negative intersection point. So we can do it in an orientation preserving way. And what you get at the end is a smoothly embedded sphere. So the real answer of the genus function of 2CP2 on 3, 0 is actually 0. So the formula is not that great. Okay, let's take another class. How about 3, 1? So what is N31? Well, this is still a torus. This is a sphere. So the naive bound is 1. And I claim that this is also 1. So how can we check that? Well, the argument is kind of classical. So suppose that in 2CP2, this class 3, 1 is represented by a sphere. So the sphere is somehow, it's a complicated sphere. I try to draw a complicated sphere. This is an S2. And the self-intersection is 3 squared plus 1 squared. So C is just 10. Okay? So now we do the following. We blow it up 9 times. So blow up 9 times. So we get something in 2CP2, connected some 9CP2 bar, and we have this sphere with, so let's put a tilde, we just take the strict transform with self-intersection 1. So the tubular neighborhood in this sphere is just the punctured CP2. So we just remove that and we get a manifold X. And what are the two properties of X which we would like to use? The first is that we can compute the signature. So the signature was 2 here. We blew up 9 times, so it became -7. And then we removed one positive guy, so the signature is -8. That was easy. The other part is a little more complicated. I claim that it is spin. Why is it spin? Well, the secret is that this class is a characteristic class. It's like, it's the mod 2 reduction of the Poincare dual is just W2 of the 4 manifold. So you can imagine that somehow W2 is concentrated in the neighborhood of that sphere, and what's left over for the rest of the manifold is like nothing. When you blow up, you always blow up the sphere as well, so this property just holds for C tilde as well. This is also characteristic, so the W2 is concentrated along that sphere, and now you remove it. So what's left is just W2 equals 0. So this is spin, and now we invoke, this was a smooth construction, and then we remember Rocklin's theorem saying that if you have a spin 4 manifold, then the signature is divisible by 16. Algebra would demand divisibility by 8. That's what algebra tells you, and smooth topology forces the divisibility to be by 16, and that's a contradiction. So we started with a sphere, and we got a 4 manifold which doesn't exist, so the sphere better not exist, so the minimal genus is 1, which we can actually present by taking a smooth torus here and the sphere there. Does that make sense? Okay, so that's great. We can use this theorem to prove the following. Corollary. Figure 8 knot is not slice. And the proof is up there. So let me just explain. So proof is in the whiteboard. So we start with a twice punctured CP2, twice punctured 2CP2. So this is 2CP2 minus 2 disks. Of course, the interior of the 2 disks, but it's okay. So this is S3, and this is S3, and I draw the figure 8 knot here. That's what you see up there. So figure 8. Now I claim that there is an annulus going through this camel-shaped object, which goes to the unknot, and the annulus. So A is an annulus representing the class 3-1 in the relative homology, but the relative homology happens to be the same as the absolute because the boundaries are just S3s. Okay, so how can we see that? Well, the CP2 is just given by these two, whoops. By these two +1 framed unknots. And so we start with a trivial annulus, and then we just attach the two handles along those circles as they are drawn. You should notice that the black curve is exactly the same as this one isotope, sort of mildly. So now comes a little yoga. You have to blow down the +1s, and I hope we got it right. You will get the unknown. So that's, I hope you see the annulus. It's just the trivial annulus, add the two handles, and then see what is the knot in the new boundary S3. Okay. How can I tell which homology class we are hitting? Well, this depends on the linking number of the knot and the 2 + 1 framed circles. And for that, you need to orient the knot, and I forgot to orient the knot. But say it's oriented like this, so it goes like that. It comes up, it comes down, like this, like that, and where is, no, yeah, it's okay. So it links the upper circle once and the lower one 3 times. So it's really, wow, maybe 1, 3 or 3, 1 doesn't matter. Okay, so where is the contradiction? Well, now I close this manifold up and I really get 2CP2 and I can finish it with a disk. So I get a disk, and if the figure 8 were slice, then I would represent the class D1 with a sphere, which would contradict my previous argument, and it would contradict like the Brocklin's theorem. That's too bad. So then you could say, okay, so what a fantastic corollary. Of course, this was known. If you pull out the Fox-Milnor condition, and it takes like, I don't know, maybe 22 seconds of calculation, you can convince yourself that the figure 8 knot is not slice. But the power of this story is that you can do the same with another knot. So consider now the 2-1 cable of the figure 8. Why is this an interesting knot? So it has been shown in the mid-90s. So let's put it K. K is not ribbon. So people only hope that it will be a slice knot, and that would put an end to this, I would say, centuries-long conundrum. Well, starting from the 60s, whether all slice knots are ribbon. This is what's called the slice ribbon conjecture, and this is a confusing conjecture. Ribbonness of a knot, you feel that it's like a 3-dimensional property. Sliceness is a genuinely 4-dimensional thing. And we 4-dimensional topologists are absolutely convinced that 3D is much simpler than 4D. So it shouldn't be the same. With that said, we don't know any example of a slice knot which is not ribbon. Here is a knot which is not ribbon, so you hope that it is slice. Well, the fact is, so this is a theorem that K is not slice. So we have to search further. So this was proved by Irvin, Dye, and then a bunch of other people, which I should not be able to recall their names. But here is another proof of that, using that principle. So just take the 2-1 cable, which is just to say that you just double, except at one point, this doubling will be twisted like that. So this is a new knot, and just copy everything here. So I would just double, and in one slot, I do this. Otherwise, everything was just parallel to the drawing. Well, when you do the yoga, so first of all, instead of the class 3-1, it will be the 6-2, because now it will link the lower circle 6 times, and this guy 2 times. And this knot, instead of the other knot, it will be the 2 - 19 torus knot. Somehow the right will come in. Okay, so I can use my previous figure. I take K here, and this is a torus knot, 2 - 19. That's good. Now, it doesn't bound the disk, but it does bound a genus 9 surface. So what we would get, if the knot is slice, we could say that, so here's proof. If K is slice, then 6-2 can be represented by the genus 9 surface. Well, that's a possibility. Let's see what is the naive bound, the naive guess for that homology class. So the naive gas for 6,2 is, so you apply the formula here and the formula there. This gives you 10, this gives you 0, so that's just 10. But we don't know whether the naive gas is the right one, whether it really gives the minimal genus. And here's a theorem. This is of Jim Bryan from 97. That the minimal genus function of 2CP2 on 6,2 is indeed 10. So this is where we would use gauge theory, but you might say that, well, this manifold is absolutely not designed to apply gauge theory. It has the wrong B2 plus, probably everything is 0. And you are absolutely right. We are not doing the adjunction in this manifold, rather, so I will just give you the sketch of the proof. Of course, at the crucial moment, I will just stop and leave it. But so here's the sketch. Suppose sigma in 2CP2 represents 6,2. So, 6,2, and then there is this sigma, which is a very complicated genus G surface. So what can we say about the genus? So the idea is that take the double branch cover. Now I will make a few statements. So the first statement is that cover and call it X. So X is spin. Why is it spin? Well, the lesson is that if you have a class, which is, it has to be twice something to construct the double branch cover to begin with. But if it is twice a characteristic class, then the double branch cover will be spin. Sigma is twice a characteristic. So that's sort of an overall principle. H1 of X is finite. Again, this comes from the theory of branch covers. We can compute the Euler characteristic. The Euler characteristic of X is just twice the Euler characteristic of 2CP2 minus the Euler characteristic of the branch set. That's very simple Euler characteristic computation. And in this case, I computed at home, and now I don't know where it is. It's, I think, 2G plus, this is important, so. Yeah, but I didn't write it there. So anyway, it's either 4 or 6. We will see which one works for the group. And then the signature. So the Euler characteristic really only depends on the Euler characteristic of the base and the Euler characteristic of the branch set. The signature, however, only depends on the signature of the base, twice the signature of 2CP2, and then the self-intersection of the branch set, it's 1/2 sigma squared. In this case, that's just minus 16. So this already gives, I think it's 6. And so maybe I erase that. So we will get sharper and sharper estimates for G. So the first is that, of course, B2, which is now 2G plus 4, is always bigger or equal than the absolute value of the signature. Now they are both defined on the second homology, say with real coefficients, so the dimension is always bigger than the absolute value of the signature, right? One of them is the sum of the B2 plus and the B2 minus, the other one is the difference of the two. Okay, so that already gives something for G, right? this is like 16, so G should be bigger than 6, at least 6. Good. Then there is this principle, or well, this is not a principle. This is where gauge theory comes in. There is Donaldson's theorem that if X is spin and the B2 plus is 1, then B2 is 2. And indeed, he claims that the intersection fold is just the hyperbolic pair. So now, what happens if, well, that will not happen, but if B2 plus is 2, then B2 is 4, and the intersection fold is 0, 1 plus. So this is like Donaldson's theorems B and C. Theorem A is when the B2 plus is equal to 0, so that's the diagonalizability theorem. This is what he got the Fields Medal for. These are just sort of leftover theorems. So these give further constraints. You can drive it all the way up to G being at least 9. But then this is not good enough, right? Genus 9 is allowed by this not to being sliced, and this is where Bryan's theorem comes in, and he shows that the double-branched cover, we just used topological properties of this manifold, but it comes with a non-trivial Z2 action because it's a double-branched cover. And getting that Z2 action into this gauge theoretic setting, he was able to improve it by 1. And of course, the naive bound, which comes with a construction, shows that it can be realized. So that's the answer. But that also shows that there is no way I can put this on that knot, because that would give you genus 9. So that knot is not sliced. Okay, why did people expect this knot to be sliced? This 2-1 cable, well, it's hard to tell. Here is my version. So somehow the figure 8 is not sliced, as we just proved. But if you take 2 figure 8s and you connect some of them, this becomes sliced. This is a generic phenomenon, but if you take a knot and its mirror image and connect some, this is a sliced knot, and the figure 8 is its own mirror. So 2K, 2 figure 8 is sliced. And well, this is also some kind of 2 figure 8s, not disjointly, but drawn parallel and then hooked up. So, philosophically, it would not be such a surprise if this is sliced. Philosophically, it's not sliced. So that's the end of this story. And we have to figure out other knots which give the counterexample to the sliced ribbon conjecture. Okay.
Do you know the proof that K wasn't ribbon from the 90s?
Whether I know the proof?
Yeah.
Okay, I say, yeah, I do. Now it's your turn. I did read the proof. Would I be able to present it? No. And
what does it use? What's the abstraction to being?
Okay, I changed my answer. No, I read the proof and I don't remember. It's like some, so you construct some handle body embedding, but I don't remember. I did read the proof, and I should look up the reference. Maybe I have the reference, or maybe not. Miyazaki. '94. I should admit that I keep forgetting my own papers, so okay. So the genus function on the K3 surface. What can we say about that? Well, we see a lot of surface in the K3. This is probably the most studied complicated surface in 4-dimensional topology, and we know a lot of stuff, so I will ask a very simple question. So what are the spheres in K3. Or let's simplify that. What are the self-intersections of embedded spheres? Just the numbers. So the adjunction formula tells you that if you have a sphere and you take the self-intersection, then it should be non-negative, non-positive. So positive spheres would kill the Seiberg-Witten variance. On the other hand, this is a symplectic manifold which has a basic class. You can write down the adjunction and it will give you that for a sphere it cannot be positive. Indeed, it cannot be. So by a slightly more sophisticated argument, this is also impossible. Also, we know that the K3 surface is a spin, so every self-intersection should be even. So there might be some even negative numbers. So here is a fact. We have examples for -2, -4, all the way down to -86. And then this is where it stops. And the question is the absolute value of S bounded or as an embedded sphere in the K3? We don't know the answer. I would love to know the answer. Instead, what I will do, I will try to convince you that there are these spheres. Actually, I will just focus on the sort of the tail of this sequence, -86, but as a warm-up, we will start with -82. So, yeah, that's, okay, so how can we construct spheres? Well, first we need to construct the K3 surface itself. So let's do the following. As always, we take S2 cross S2. And now we take two vertical and 4 horizontal spheres in that 4 manifold, and we take the double branched cover. Double branched cover, and this will be my X. Okay, so there is a little problem. There is this principle that if you take a smooth curve, which is divisible in homology by 2, you can take the double branched cover and it will be a smooth 4 manifold. This curve is not smooth. It has all these transverse intersections. So these will give you singularities in this 4 manifold. So we don't like that. So we rather do the following. We start with the same. And then first, we blow up these intersection points. So blow up 8 times. So we get a slightly more complicated 4 manifold. This is S2 cross S2 blown up 8 times. And then we have these 2 guys, and there are the 4 horizontal ones. But now they become disjoint because they were sort of transverse intersections. When you blow up, they get separated. And there are these -1 curves, the exceptional divisors. If you blow them back down, then you get exactly this. So far, so good. So now, these were spheres of self-intersection 0. Now this has been changed. The vertical guys were blown up 4 times, so they are -4 curves. The horizontal ones -2. And there are all these 8 -1s. And now we take the double branched cover. And we get a manifold X.
Over what?
So over the strict transform of the previous, which happens to be again an even class. Okay, so that's good. So we should understand what this manifold is, and we should note that it comes with a fibration. Namely, there is a projection to S2, and the generic fiber is just a torus. It's a sphere. Sorry, it's a sphere, and when we take the double branched cover, again, this is the generic fiber is a sphere. which is hit 4 times by the branch locus. So this has a map to CP1, and the generic fiber is a torus. So this is the kind of thing we call an elliptic fibration, and it has 2 singular fibers. Over the 2 points where we pick the vertical S2s, we will get singular fibers. How do the singular fibers look like? Well, we can predict that. So there is this -4 sphere, which is in the branch locus, so it will lift to a sphere, but the self-intersection will get its half. So there is a -2 sphere, and then there are these -1 guys, which are branched in 2 points. And the sphere, the double branch cover of the sphere branched in 2 points is also a sphere, but now the self-intersection doubles. So there are these -2s, 4 of them hanging out. So there are 2 such fibers, and all the other fibers are just regular nice tori. Okay, so we have 2 of those. What is this 4 manifold? So we see that it has a fibration over CP1 with 2 very singular fibers, and the others are just tori. But we can predict what this 4 manifold is because there is also another projection to this direction, right? In the base manifold, which gives us a projection down here, also CP1, in the double branched cover. What is that? What's the fiber of that fibration? Well, those are spheres which are branched only in 2 points. Those are spheres. So this is a CP1 fibration over CP1, and it has 4 singular fibers, and the singular fibers are like, so there is this horizontal -2, which is in the branch locus, so it will become a -1, and 2 -2s hanging off. Those guys can be blown down, and then you will just see that X is actually S2 cross S2 blown up 8 times. You know, it's the same. Somehow it's insane, but this is what it is. Which is just CP2 blown up 9 times. And you have to remember that the K3 surface is constructed by 2 of these taking their fiber sum. So my K3 has a fibration over CP1 where it has 4 singular fibers. Right? So immediately we see a lot of -2 spheres. So we can play with those, like how can I get a -4 sphere? Well, I take 2 disjoint ones and then I just tube them together. And the -6, -8, and so on. So you will see a lot. Indeed, there is one more curve I would like to carry on. There is this -2, which in the double branched cover will become a -1, but I take 2 of them, so there will be one further -2 curve, which is just a section of this fibration. So now instead of drawing this, I will go to the dual picture where the spheres are denoted by dots and the intersection by edges. And so we have the section, and this connects to this little star, or what is it? You know, there are these Star Wars movies where like they are driving these destroyers or whatever. So we have, and everybody is a -2 sphere. And this one is bad, and this one is bad. No. Yeah, this was okay, and this is, sorry. Okay, so now you have how many? It's like 21 -2 spheres. And now it's sort of easy to construct a -82 sphere. What you do is you just take them with signs in such a way that all intersections are negative, and then you just take the square. And can you do that? It's up to you how to pick the orientation. And this graph is a tree, so you are absolutely free to take the orientations of the spheres. And I take those where all intersections are are negative, and you know the formula, but I will write down because. And these terms are all -1 or 0 if they are not connected. So it will really drive down the intersection, and you will get a -82 sphere. This is not the best possible. If you are familiar with the theory of Lefschetz vibrations, how do we do with time? Okay, so 1 more minute. If you are familiar with the theory of Lefschetz vibrations, then this elliptic vibration has total monodromy AB to the 12, where A is a Dane twist along one circle of the torus, and B is sort of the orthogonal circle. And this presentation just utilized that AB cube, which is minus the identity, to the 4th is actually the total vibration. And this 4 symbolizes the 3 singular fibers here. Well, of course, 12 is not only 3 times 4, but it's also 4 times 3. So we can take AB to the 4th cube, and that's the same. So by some different construction, we can get a vibration where by K3 fibers over CP1 by 3 singular fibers, and these singular fibers will look like this Dynkin diagram. So it has like 7 vertices. We have 3 of those plus the section, so we can improve this to 22, and this gives -86. Can we do better than that? I don't know. I would love to see that. Actually, I would love to see both. Either a proof that we have a -88 or -90 sphere, or a proof that we don't have that. Both would be very exciting. And this is the moment I will stop. Thank you very much. No -90 spheres.
I want to ask a question about the theorem by Brian. He used some technique to compute the minimal genus of the class 2-6. Is there any other class in TCP2 that are known for their minimal genus?
There are a few. They are sort of random classes, and what happens is that, so let's call, what did I call, D1, D2, and then what happens is that we have so the gas, let me give the gas, and this gas is verified in some few cases that if one of the coordinates is like 3 times the other, then probably the naive gas is right. And if it is bigger than that, so it's like D2, but this is bigger than 3D2, then the difference between the actual and the naive gas can be arbitrarily large. And if it is smaller, then we don't know. So we have a few scattered results, and if one of them is way bigger than the other, then we can improve the naive bound by an arbitrary amount by driving D2 larger and larger, but we don't know the answer. This would, a good understanding of the minimal genus would actually help us to attack the problem of not only the 2-1 cable, but say the 4-1 or the 6-1, but we don't know how to do that. Yes?
I'm seeing how, maybe I just missed it, but like when did you use the CP1 vibration? It looks to me like you only need the like elliptic vibration on X, but I know you can also get the like one with CP1 regular fibers.
So when I try to identify what the manifold is.
Oh,
so,
okay.
I mean, of course, it's a fantastic definition. Take the double-branched coupler. And then you might ask, what the hell is this manifold? And then it's hard to answer, except now we have this other vibration, and we do know that it's a CP1 vibration over CP1, and we know the singular fibers. We blow them down, and there are only 2 CP1 bundles over CP1. Yeah. And actually, it doesn't matter which one you end up with. It will be determined by how you blow down. You blow down this middle one, and then you have to always choose left or right. If you take an even number of left and an even number of right, you get S2 cross S2, otherwise you get CP2 blown up CP2 blown up in one point. So that's only like to identify my manifold and to see that if I take twice, then this is exactly my definition of the K3 surface.
Maybe a general question are there examples of exotic four manifolds that have the same genus function?
Not that I know of. So there are these, what we call fake S2 cross S2s. I mean, if there is a counterexample to the Poincare conjecture, that would be a fantastic but very trivial example. There are fake S2 cross S2s, which have the same rational homology as S2 cross S2, but maybe non-trivial fundamental groups. Or we have a construction of infinitely many, they have the same genus function. They might have, some of them might have the same fundamental group. They might be homeomorphic, we don't know. So there is no really solid example of that I know of. But I would not be surprised if there are exotic manifolds which have the same genus function. The genus function shouldn't contain all the information. It has to be defined. And this is where I propose this, also the slice, the size general. Okay. Well, that's it.
I think a quick announcement, you all should have gotten an email about what's coming up next week, and it also contains a little Google form about whether you want to go on the new trip, and please fill that out.
Sounds fun.
If you're leaving today,